Hello everyone, welcome to part 3 of the chapter 11 videos where we're going to still be talking about making inferences with two means, which means especially we're going to be doing confidence intervals and hypothesis testing. This time though, we're using independent samples. Now since it's means, we're still talking about t-test and also t-interval because it's having to do with means, but in this case since the samples are independent, we are looking for the one where we're having two sample for these things, two sample t-test and also the two sample t-interval. And then we can see here what kind of symbols we're going to be using. Of course we're using mu since we're talking about mean, and so the proper symbol for the parameter for mean is mu. And then our hypothesis, predictably the null hypothesis, should always have the equal sign. But here we're not going to, like we did in section 11.2, we're not going to be able to do the mean differences anymore because these two samples are independent, which means the samples might not even be the same size, so there's no way that we can, by pairs, find a difference because, eventually you're going to come up with some data point that doesn't have something paired with it, so there's no way to take a difference. We're going to just continue referring with mu1 and mu2 separately like this, and so our null hypothesis would be that the two means are the same. And then our alternative hypothesis can be that the means are different. That would be the two-tailed test, or that mu1 is less than mu2, or that mu1 is greater than mu2. So we're getting the left tail and right tail for that one. And without any further ado, I want to just come in here and try an example. There is actually one last thing that I want to mention, which is that the confidence interval, whenever we're doing the two sample t-interval, what that's going to give us, it's giving us a confidence interval for the difference of mu1 minus mu2. And that's going to come into play whenever we're interpreting whether we get negative results or positive results in terms of which one is greater, mu1 or mu2 in that case. But anyways, we have an example to work on over here. And this example, it's having to do with medicine for some bipolar disorder. There are 115 patients total that are in the study, but they're broken up into two different groups. We've got the first group that's receiving the treatment. They are with a sample size of 55, and then the other group is the remaining 60 people. And we can see right away, we can tell that this is an independent sampling because, well, for one, they're randomly divided into two groups, but also the fact that the groups are different sizes, there's no chance that we're dealing with a matched pair situation. But really, from this context, that they're randomly divided into two groups, that's what tells us right away that this is independent sampling. Now, there are some statistics that we need over here. We found that, well, in one, it's given to us that it's 55. And apparently, in the course of doing this study, we found that the mean improvement for group 1, which we can call X bar 1, that is 14.8. And then the standard deviation for that group is 12.5. So we would say that standard deviation, which is the little s when it's with a sample, S1 is 12.5. And then we're getting the similar statistics for this one. The group size for group 2 is 60, and then X bar 2 is going to be 8.1, and standard deviation number 2 is going to be 12.7. And what the problem is asking says, does the evidence suggest that the experimental group, which that is group 1, experienced a larger mean improvement than the control group, which the control group is group number 2. And we're looking for group 1 to have a larger mean improvement. And so when we're making our hypotheses over here, the null hypothesis will be that the mean improvements for these two groups are the same. The alternative, what we're testing, is whether group 1 had a larger mean improvement than group 2. And so this would be the right tail test. And what we're going to do is we're going to go in here, stat, we want the two sample t-test. T-test, of course, because it's with means. And then we have the particular stats. We don't have the data from this test or from this experiment. All that we have are these statistics that the X bar 1 is 14.8, and I'm just going to be entering these here as we have them from this table. Sample size was 55, and then with the control group that had the mean of 8.1 with the standard deviation of 12.7, and the size of 60, we're testing whether mu1 is greater than mu2. So it's the one on the far right. Pooled, we always just say no, and now we're going to calculate it. And we end up getting a test statistic for the t-value. Sometimes we'd be interested in this, is 2.85. We're looking for whether that falls into the critical region on the t-table. The t-table, it is in the formula chart, but I'm just going to look at this p-value because the p-value is this number here, the 0.0026. I'm going to scoot over a little bit, 0.0026. Now, since we are at the 0.01 level of significance, so alpha is 0.01, we're comparing the p-value versus alpha, and since our p-value of 0.0026 is less than the alpha value, that means that we should reject the null hypothesis. And that means that our conclusion, we are concluding, again, we're not concluding that for a fact or that we proved that the mean improvement for the experimental group or for the treatment group is greater than the control group, but we did find evidence for that. And so our conclusion would say that there is evidence that the experimental group experienced a larger mean improvement than the control group. That's what we would want to say. But anyways, that does it for this kind of a problem. I hope that this video was helpful for you, and that does it for Chapter 11. But thank you guys for watching.